Hello, everyone. Welcome to here. I'm very excited to share this topic using Argo Workflows to reconstruct autonomous driven data pipelines. First of all, let's introduce ourselves. My partner is Yizhen Chen. He is an infrastructure engineer of Guangzhou Automobile Industrial Group, mainly focused on autonomous driven. He can't be here in person and will participate online. My name is Shuangkun Tian from Alibaba Cloud Kubernetes team and mainly focused on building data and machine learning pipelines. I'm also a maintainer at Argo Workflows. This is today's agenda. Yizhen will share the background and introduction on the autonomous driving, the challenge and the results of the reconstruction. And I will share the solution, some of the challenges and make a summary. Now let's invite Yizhen to give the sharing.
Hello everyone, I'm Yizhen Chen from GAC Group. I'm glad that I can join this event remotely. Today, I and my colleague Shuangkun Tian from Alibaba, we want to share how we reconstructed the data pipeline of our autonomous driving system using Argo Workflow. Let me briefly introduce our company and business for those who are not familiar with GAC. GAC Group is a leading automobile manufacturer in China. It sells about 2 million of cars every year. Recently, we are trying our best in building an end-to-end autonomous driving system, and we plan to launch mass production of vehicles with our system next year. So to achieve this goal, we have to collect and process massive amount of data to train our models. And so we have these pipelines. As you can see, we collect sensor data from our test vehicles, we process them to prepare data for training, we label them for ground truth, and we mice valuable scenarios for training, and then we train our models. After that, we test the model in simulation and finally deploy the models back to the fleet. So this is a quite complex data pipeline, and it's difficult to manage such a pipeline. And I summarize the main challenges of our data pipeline as three aspects. First is scale, second is complexity, and the third is agility. For scale, we have TB of data to process every day, and occasionally we need to process PB of data in a batch job. So we need to process it in a distributed manner. And since the data volume is growing fast, we need a system to be able to scale up easily. For complexity, as you can see on previous slide, the pipelines are intricate DAGs with many steps, with different data types and mixed CPU, GPU workloads. And for agility, our models are in a rapid development process, and we need to adapt our pipeline for constant new requirements. So we need the system to be agile. But commonly, something is complex and with a large scale is not agile. So how are we going to address these challenges? We believe Argo Workflow is a good choice for these reasons. First, it runs natively on Kubernetes, leveraging its robust scaling, scheduling, and resource management capacities. So it's good max parallel processing. Its declarative DAG fits our complex multi-step pipelines, and it provides visualizations and logging for workflow, making debug much easier. And it's a container native, which is good for rapid iteration and testing of each component. So now let me share some real problems we encountered and how we solved them. The first case is on raw data processing. As you can see, this pipeline is straightforward. We prepare a batch, then we fan out to process each raw spec file in parallel. Each batch goes through stage like image and distortion, leader motion compensation, view transformation, and finally, we segment the data into clips. But the problem is with increasing data volume, the pipeline needs to improve its throughput and reduce processing time. Otherwise, the speed of processing cannot keep up with the data growth. To address this, we implemented several optimizations. First, we streamlined our multi-stage pipeline. We processed the result directly between stages to avoid collecting full dataset between steps, which may cause bottleneck. And then we work on the processing time variabilities. If one node is long processing time, it may slow down the entire pipeline. So we need to identify and optimize these steps. For example, when we do object motion interpolation, the time may change based on the number of objects detected and the duration of the record. So we identified these steps and then optimized them. We also apply computational performance optimizations like vectorization and new bar compilation and doing some caching. We are still looking for ways to further accelerate the pipeline. When we are trying to scale horizontally our workers, we met a challenge. If one batch has 1,000 workers, each worker needs to download its raw data, which is about 2 GB back file. That is 2 TB of data that we need to download on the same time from our shared object storage. So the storage layer will become the bottleneck. This is one of our challenges. And the second case is about GPU utilization on our cluster. Our auto-labeling and backfilling tasks need to use GPU to run inference. Unlike training large language models, the labeling and perception model is relatively small, so it can easily fit into a single GPU. So the challenge is how to maximize GPU utilization to have a higher inference throughput. We use GPU sharing to run multiple tasks on a single physical GPU, and we also applied model quantization and other techniques to increase the batch size so we can process on a single GPU to achieve a higher inference throughput and better GPU utilization. The third case I want to share is about the heterogeneous workload on our clusters. As illustrated in the diagram, our original simulation required 2 kinds of components, which are tightly coupled within a single pod. There is the simulation engine workload, which handle physics, traffic, and scenario logic, and algorithm workload. So the algorithm workload is updated to our newest learned model, which requires GPU resources to run inference. So when we run a simulation on a scenario, we got a mixture of CPU and GPU workloads. If we run it in a single pod, which will be scheduled to a single node, the CPU to GPU resource ratio is may not be the same as the ratio of the underlying hardware. So it leads to poor GPU utilization. So we solve this problem by decoupling. We split these components into separate pods so we can place the engine workload on a CPU node and the model workload on a GPU node. So this helps to optimize utilization of CPU and GPU resources. However, our CPU resources are highly elastic thanks to Alibaba's serverless Kubernetes cluster. But our GPU resources are not that elastic, so we're still facing the challenge from peak load pressures on our heterogeneous cluster, which means every time the model is updated, we need to run thousands of scenarios in parallel, leading to high load pressure. So now let's discuss our multi-tenant difficulty. As you can see in the diagram, to build an autonomous driving system, we need teams working together: perception, planning, data, and simulation. Each team has its own workload and pipelines. The workload of each team has different requirements. Some tasks are high priority, but others are not. And some require batch processing, others need constant data ingestions. So we need a unified resource management and scheduling platform, which enable teams to share resources for higher efficiency and better resource utilization. In the meantime, we need to ensure critical tasks get dedicated resources if needed. So this is also a challenge for us. With close collaboration with Alibaba Cloud, together we made significant progress. Our team at GAC focused on pipeline level optimizations, like we streamlined the workflow, we quantized the inference model, and decoupled workload. Shuangkun's team at Alibaba Cloud tackles the infrastructure side for better scheduling, concurrency control, GPU sharing, and storage acceleration, etc. And now our data pipeline can handle millions of the bag every day, consuming thousands of cores and using hundreds of gigabits per second of storage bandwidth. We achieve higher throughput, lower cost, and better resource utilization. So now I will hand over to Shuangkun to share some details in depth on how we solve the challenges I mentioned and how we build this high-performance system. Thank you.
Thanks for Yizhen's sharing. As you can see, Argo Workflows has applied to a wide range of these scenarios, including data mine, perception, solution, etc., and the reconstruction has achieved great results. Next, let me continue to introduce some of the solutions to the challenges mentioned earlier. For multiple teams and large scale, we use concurrency control. For automation, we build an event-driven mechanism. For resource utilization, we implement a hybrid scheduling pipeline. For storage slow access, we use cache to speed it up. Next, let's dive into the details. For concurrency control, the Argo controller provides abundant capabilities from global level to workflows level. In terms of global concurrency, we configured a unified concurrency limit to prevent the entire cluster from crashing overlap. At the namespace level, we allocated independent concurrency resource for different service, and at the same time, it can isolate in different namespace without interfering with each other. For specific large-scale tasks and high priority tasks, we can also adjust parameters and concurrency for optimization. Based on this concurrency control mechanism, we can well protect the entire cluster and lets multiple teams share the concurrency resource of a single cluster. Let's move on to the event-driven. As a leader in Chinese automobile manufacture, GAC Group has a very large number of cars on the road, generating huge amounts of data every day. To avoid lots of manual errors, we built an event-driven mechanism. Argo Event is an excellent tool that supports more than 20 event sources and can integrate with Argo Workflows seamlessly. Based on different event sources, raw data connect to the object storage service and signals upload to the Kafka. We have built a full automated pipeline with Argo events and workflows. It can automatically trigger tasks such as data mining, auto-labeling, inference, and greatly reduce the manual work and make the pipeline more reliable. Let's continue for the scheduling. Different business has different resource usage characters. We built a hybrid scheduling pipeline based on these characters. For CPU-sensitive tasks such as data processing, we use a serverless resource provided by Alibaba Cloud ACS for quickly processing and reduce costs. For GPU-required tasks and lightweight and in a lightweight scenario such as inference, we have built a CPU shared scheduling strategy based on the open source project coordinator and Hami. Allow the multitasks can be deployed on the same high-performance CPU, improve overall resource utilization. At the same time, the project resource can be escalated. For GPU-sensitive tasks such as simulation, we reserve the resource and achieve topology-aware policy to scheduling the tasks to the same PCIe or EV-Link nodes as much as possible. Through this design, we got a higher GPU utilization and improved performance. Meanwhile, various types of business can be orchestrated in the same pipeline, enable collaboration for each task. Next, to address the slow storage access, we adopt the cloud-native storage acceleration system Fluid. Before running large-scale tasks, we create cache datasets of image and data. Once the caches are ready, we start large-scale parallel processing. With this approach, we support 200 GB of the bandwidth and greatly shorten the execution time of the tasks. Especially for GPU-based tasks, there is no need to spend lots of time to pull in images, which also directly improves the utilization. This is our overall system architecture. The bottom layer is the resource layer, including computing and storage resource such as CPU, GPU, serverless pod, and object storage service. The middle layer is orchestration engine centered on Argo Workflows and integrated with cloud-native enhancement capabilities, including event-driven, hybrid scheduling, and storage acceleration. The top layer covers phone link scenarios in autonomous driving pipelines, including perception, data mining, auto-labeling, simulation, inference. The platform is flexible and easy to scale. Next, let's make a summary. Today, Yizhen shares the journey reconstruct autonomous driven data pipelines with Argo Workflows, and I shared some of the approach to address the challenge we meet. We jointly built an autonomous driven solutions based on Argo Workflows. The solution both flexible and efficient, not only at the infrastructure level, but also in the business level. Enable the teams to decouple workloads and apply optimizations like model quantization, streaming pipelines. As a result, the collaboration between GAC Group and Alibaba Cloud achieved scale, millions bags per day, thousands of CPUs, efficient 40% increase in GPU utilization, and 200 GB bandwidth, agility, 17 reduction in operational cost, and can support multiple teams quickly. Therefore, we can conclude that Argo Workflows is very suitable for autonomous driving scenarios, even though these scenarios is complex, challenging, and emerging industrial. I believe that Argo Workflows can also be applied to many more complex scenarios. If you also have needs for orchestrating complex pipelines, helping the case study from Guangzhou Automobile Industrial Group and Alibaba Cloud will be help to you. Thank you. Thanks.